So before we get into the new concept, I wanted to take a second and revisit essentially what we've learned so far about these different methods to solve a differential equation. So we've got three approaches so far that we can address and handle. And the reason why I want to take a second and do this is we're about to learn how we can connect some of our algebraic manipulation techniques, so from maybe pre-calculus, maybe some college algebra skills, some things that we've learned that we can rewrite an expression and then utilize it to do one of the formats we've seen. So let's be real clear about what formats we have covered. So the first format that we have seen is called separable equations, and the idea there, and I'm just going to give a brief 30-second reminder of this, is we have a differential equation where I'm allowed to separate out the x function and the y function so it looks like some sort of product, and then we would essentially rewrite this so that we have a function of y on one side and a function of x on the other, and then we would integrate both sides, right? So we would redefine this 1 over h of y to be some function p of x, or p of y, I'm sorry. Dx. Okay, so that was one method that we have encountered so far. Okay, then we have the linear equation method. So the linear equation method says if I can get the equation to look something like dy dx plus some function p of x times y equals some other function of x, then I find what's called an integrating factor. Sorry, that's e raised to the integrating factor of p of x dx. And we end up, whatever that expression is, we end up just multiplying the original equation by that expression, and then by applying the product rule, we end up having a solution. So that's that technique. And then the latest technique that we've seen is this idea of using partial derivatives. So we say that there's some function that the partial with respect to x we're going to call m of xy, and the partial with respect to y we're going to call n of xy. And so if I have a partial derivative that I can write in this format, dy equals 0, right? So I have a partial derivative, kind of generally looks like that. And first I explore that, well, if that in fact is true, that m and n are partial derivatives of some overarching function, then the second derivatives should match. So I take the second partial of m and n, see if they match, and if they are, then I integrate one of the two expressions with the appropriate variable choice. Okay. So those are the three techniques, those are the three methods that we have encountered so far. So as we start looking at methods of substitution, that's kind of our goal, is to get it to look like one of those forms, and hopefully something along the way can happen that we are able to manipulate the expression so that we can go with one of the three known methods to solve the differential. All right, so that brings us to the new idea, and that is something involving a homogeneous equation. So let's first define what homogeneous equations look like, and then we can talk about how, what does that have to do with anything in the T of China. So, all right, so a homogeneous equation is an equation where I have a constant or a variable expression or something that I can factor out of the original function. So if a function f possesses the property where f of tx comma ty is such that t raised to some alpha essentially can be factored out of the function, then we say that this function is homogeneous to the degree of that alpha is. So quick example, f of x equals x cubed plus y cubed. If I replace x and y with tx and ty, It's that fact that I can factor out the t and I get a t cubed on the outside that makes that homogeneous of degree 3. Okay. The other example that's not homogeneous, it's that plus 1 that's the issue, so I can't really factor anything out of it. Okay. Then we additionally throw in this definition that if I have an equation in differential form, we can define it to be homogeneous if m and n itself are both homogeneous of the same degree. But what I want to draw your attention to as we start looking at this first example is I'm trying to figure out a way for my substitution. So I'm trying to find something I can substitute in that will allow me to factor something out of every expression in the parentheses. So as we start drilling into these specific examples, and you're thinking, gosh, how would I decide what would be a good substitution to go with? The answer is you're trying to find something that you can factor out. So kind of use that as a model and guideline. Okay, so that said, let's do something.